understand the FPGA design flow, right? Maybe it will be little bit of helpful for those. I think it will be helpful for hardware designer also who are designing any embedded applications using FPGA. It will be also helpful for someone who is writing the FPGA code or VSDL code, okay, or RTL code, okay. So let's understand. So you understood what FPGA is, what are the configurable logic block, what is the switch matrix, what is the IOB block, okay. So you understood overall what FPGA is, why, how it works, right? How you configure FPGA for different functionality. With that, right, how how the flow, design flow happens when you are doing any FPGA hardware, right? So you will have any requirement specification, right? Either from customers or either for any industry you are working, right? Whether it comes from your manager or anyway technical requirement. So you will have a technical requirement. Based on that technical requirement, you will create some kind of architecture. For examples, what here you can see, there is some external memory interface, okay. It can be RAM or anything, and you want to read those or interact, basically interact or communicate with this memory using a FPGA device, okay. So what do you do in FPGA? What you are doing, you are implementing all these logic block. You are implementing this FIFO, okay, read, write, FIFO, and these are the commands, okay, for reading and writing, and command for controlling. And how do you are using? You are using some XI interface. XI is nothing but kind of a chip to chip interface, okay. And so you are using these all logic blocks inside your FPGA, okay. So based on the requirements, you create architecture, kind of a block level diagram, how it, and then after discussing with all your stakeholder or architecture, the finalization of architecture, you go with the design entry, right? Then there are different ways for design entry. One is that you write a VSDL or Verilog code. It is nothing but a kind of a RTL code. Okay, basically, kind of you can use different tools. You can use a Quartus Prime, okay, basically from Intel, or you use a Vivado from Xilinx. There are other tool also for doing this VSDL Verilog. There is also another way, like you do the schematics. By that also you can do that. But for now, okay, let's understand that. Um, After your architecture is finalized, you can do the design using these methods. Writing a VSDL. VSDL is nothing but it looks something like this. Okay, you have a module where you define your all the inputs or the outputs, right? And then these are some signals, and then this is some logic function, and gate, or gate. This is very log. This is not VSDL. VSDL and Verilog syntax are a little bit different, okay. So but people say that Verilog is a little bit easier because it looks something like C language. That is why it is easier. VSDL is little bit difficult, okay. So you do the design entry using this, okay, VSDL or Verilog. Once you do the design entry, right, whatever the code you have written, right, you do the behavior simulation. Behavior simulation is nothing but what you are trying to do, whatever the VSDL code you have written, and what was your requirement, right, or what was your design intention, right. So behavior simulation is nothing but you try to make sure that you want to simulate the behavior of this RTL or the VSDL, whether it is working as intended or not, whatever you have expected, right? If you are writing any full adder or half adder circuit, right? So when you do the simulation, you understand whether it is working as full adder or not, okay? And for that, you do the behavior simulation. So if it is working at if the working is okay, you move to next stage. Otherwise, you go and change the design, whatever you have done. There must be something wrong. and you can, these are some simulations you can see right here. You can see your input ABC, and these are nothing but kind of a value. You can see 0 1 2 here. You can see right here, like for A and B, the input is A 0 B 0, so you expect Z should be 0. So you can verify this using this behavior simulation. Once this is done, right, once this is done, you move to next step, that is synthesis. Synthesis is nothing but, you understand it, whatever you have described this, right, using this boolean logic, right, you are translating those RTL code or VHDL code into the net list. Basically, the get level circuits. You see, whatever it was there, right? ABC, it is X. AC output was Y here. BC output was Z. It is here, and now you are using a OR. So it is nothing but this G4. So whatever you have written, synthesis is nothing but it's translate these logic into the get level netlist. Okay. Now once this is done, once you have this netlist, right? Once you have the netlist, you do the functional simulations. Now you must be asking what is difference between these behavior simulations and functional simulation. Okay, let me tell you. This behavior simulation is nothing but what you are doing. You are just simulating the RTL code. Okay, so here what happened, the codes whatever you have written, it is not compiled. Okay, it is not fully compiled. You are just checking whatever the RTL code you have written, whether it is working as intended or whether it is working as expected or not. Okay, so here timing information, whatever the timing information is there, right, setup, hold time, slack, it is not considered during this behavior simulation. But whenever you do the synthesis, okay, you see synthesis, you are translating this RTL code into the net list, but you are also using some vendor library. Vendor library is nothing but kind of, there are some design constraint. So you provide some timing constraint, okay, to this synthesis step. So synthesis is nothing but it compile the full net, like it compile the full net list and also include the timing information. Because of that, we are doing the functional simulations. Okay, to check all the timing parameter also, as well as the functionality of the design. Okay, here in this system. Now if all that is okay, right, it is functioning okay, you have also looked some the timing aspects. If it is working as expected, now you move to the next step, which is a implementation. And implementation is nothing but it contains three steps. It has a translate, map, place and route. So each steps does a different function. So what translate does is it combines whatever the netlist were there. Okay, you generated the netlist, so it combines the netlist and the vendor library, whatever the libraries are there, like design constraint. Okay, you see here I have given one snippet. This is nothing but the design constraint or the pin assignment. Okay, you see here I have written like set property pin 33, you are connecting to C out. Okay, C out signal. Okay, set property pin H3, you are connecting to port S. Okay, so these design constraint you combine with the netlist, and this translate combine all these netlist and this design constraint, and then it creates a logic design. Okay, it creates a logic design. Now here basically you are basically here whatever steps you are doing for your target device. Okay, so you are doing for your target device. Now you have created a logic design. Okay, kind of you see like of this, you have created a logic device. Okay, now what happened, there is a map, place and out. Now map is nothing but, you see, now you want to use this logic blocks. Okay, this you decided that this means you are mapping now. Okay, you want to use this logic block, this there are different. Okay, but you can configure it what to use. Okay, based on whatever simulations you have done, timing, whatever the delays, considering all these blocks I am using. This is nothing but map. Now place and route. Okay, so uh, okay, sorry, so this is place and route. Okay, place and route is okay. Now let me talk about map. Okay, you have a logic design. Okay, now here let's suppose this was the function, right? X a dash b dash c d, whatever it was there, right? So here, as I told about during configuration logic block, how you are going to translate this is called translate is nothing, map is nothing but we call it as a technology mapping. You are mapping the logic, right? So what lookup table you are going to implement this? So I here you see use lookup table f to implement x, use lookup table G to implement these all, right? So here you decide what lookup tables you are going to use, what function, what logic blocks you are going to use. Once you decide this is nothing but technology mapping. Now this is place and route. You place all those logic block in this, okay, here, okay, and then you route it, okay. So this is place and route. You see how it is routed. So this is translate map place and route. After this what you have is yeah, as I said, you have this here after this step you do all this static timing analysis and timing simulation. It is nothing but kind of you do the full timing analysis. You want to check any input output, whatever IOBs are there, input output delays. You want to check the COB, whatever the configuration logic blocks are there, those delays, gate delays, whatever the interconnect delay are there, whether it is meeting the timing constraint or not, whatever is the timing constraint, right? Whether it is meeting or not. How do you know that? Using this all simulations, static timing analysis and timing simulation. There is something called slack, right? Positive slack and negative slack. These are nothing but a kind of, it is the difference between the actual and the expected arrival time of the signal, okay. And all the setup time, whole time you check over there, okay, during these steps. After everything is verified, now what you do, you compile, you go to next step where you generate the bit stream. Bit stream is nothing but it looks something like that, what I told you, right? What is inside the FPGA, nothing but ones and zeros. And now once you have this ones and zero, so whatever your hardware you have, right, whatever target hardware you have, you can configure it using any programming method, JTAG or USB, whatever you write, okay. So this is complete FPGA design.